Okay, let's get started. Hello, I'm Stefan Güttel at the University of Manchester, and I welcome you to today's ENLA seminar. Our speaker is Elias Jarlebring. Elias is well known to many of us, but let me just give a brief introduction. And nonetheless, he is a professor of numerical analysis at the KTH in Stockholm, and he is particularly well known for his research on solvers for multi-parameter and nonlinear eigenvalue problems. And he has also made important contributions to matrix functions, matrix equations, and so on. Personally, what strikes me most about Elias' research is how he combines ideas in numerical linear algebra with his background in physics, for example, by solving eigenproblems in quantum mechanics. And today, Elias will talk about computational graphs for matrix functions. Before I hand over to Elias, let me just remind everyone that you can use either the Zoom chat to ask questions or your microphone. It might be that during the talk you need to be unmuted first. So if your microphone doesn't work, then just raise your hand on Zoom or type in the chat that you would like to ask a question. Otherwise, I'm also happy to read them out. Okay. So Elias, the stage is yours.
Thank you very much, Stefan. And thanks for the nice introduction, and thanks for having me. Yes, I'm normally like an eigenvalue problem guy, but today I have going to present another work in another topic, which also is very close to my heart, as they say. So it's about matrix functions, and this is it's a joint work with two more junior colleagues. So it's Emil Ring, my former PhD student, and Massimiliano Fassi. And so this project was initiated quite a few years ago. So I wrote here Manchester because he did his PhD in Manchester when we started the project. Then he moved to Örebro, so a postdoc in Örebro with Andrei Dimitrichin. And so at that point we already had this collaboration, and I thought, like, great, so now we are nearby, and so we should meet and like bring this project to an end. So, but then there was this little virus that came into the world, and so we didn't, although we were just 200 kilometers apart physically, we never met during his time here in Örebro. And now he has taken on a assistant professorship position in Durham. Yes, so it's about matrix functions, and this is math and software, and we have a preprint, and we also have a software package. So I have first an advertisement. Yes, so we're from the Nordic countries, so Sweden and Finland and Denmark and Norway and Iceland. We are trying to strengthen the linear algebra activities in this region. So we are organizing conferences once in a while to achieve this. And there is a conference in April. I think technically the deadline for attending has already passed, but if you ask one of the organizers nicely, maybe you will have an opportunity to attend. Yes, so I have first a couple of slides, which is mostly for the junior crowd, maybe. So it's an introduction to some things about matrix functions. So I know there are experts in the matrix functions here in the audience. I hope I will not offend anyone by explaining some definitions. And so so matrix function, we mean here of course the natural generalization of scalar-valued functions to matrices. And okay, if you want a definition, you can take, for example, the Taylor expansion definition. So our functions, the functions that I work with here, will mostly be analytic functions. And these matrix functions, they appear all over the place. And so the most celebrated one is the solution to linear time-independent ordinary differential equations are given explicitly in terms of the matrix exponential. And there are also quite a few other appearances of this. And I like this one, the matrix sign function and its applications in electronic structure calculation. So this is like a very it's an important computational challenge in quantum chemistry, molecular dynamics, and material science. So a matrix sign function is essentially something like computing an invariant subspace, and so you can see that whole many of the computations that they are doing in this field, you can see it as an evaluation of a matrix function. And so we went to the supercomputing center here at KTH a couple of years ago and asked them what they were actually computing. And it's a lot about quantum chemistry, molecular dynamics, and this self-consistent field iteration in the form where you use the matrix sign function. There's also applications in systems and control, and I worked a long time ago, or I still work on time delay systems, and you can solve some problems in stability of time delay systems with the Lambert W function. But the matrix exponential is of course the most important. And I have one quote here that I think it was Cleve Moeller who said this, but maybe someone can correct me if I'm wrong. So the success of MATLAB, or one of the reasons that MATLAB has been so successful and so much used, was that you had a very good implementation of the matrix exponential at an early stage. And the matrix exponential is also the topic of this paper, which exists in two versions, so 78 and 2003. 19 dubious ways to compute the exponential of a matrix, and then the corresponding paper 25 years later. So next year it will be 50 years. So hopefully we'll get another version of the paper at that point, maybe. Yes. So that was some topics. Okay. Yeah. In the context of this talk, I will not look at sparse matrices. So it will be matrices whose operations are closed under multiplication and left division. So large and sparse, large and dense problems, or you could also think of it as some hierarchical matrices. Yes. There are quite a few methods out there, and here is like one way to classify them, how they are derived. So you have like this Shor-Parlett type methods that use the fact that a matrix function commutes with similarity transformation, which means that you can bring your matrix to a form which is maybe easier to evaluate, for example, diagonal or triangular form. There's a lot of very nice work on polynomial and rational approximation. It's easy to evaluate a polynomial or rational function. If you can approximate your general function with a polynomial or rational function, it provides a method to evaluate or approximate your function. Quadrature methods are based on the Cauchy integral formula definition, and so you have an inverse here, and in principle you can see one method as just doing a trapezoidal rule on this integral, and those type of approaches have some advantages in terms of parallelization, since you can potentially run compute all the terms separately. And then you have these type of methods that are based on identities for scalar functions that hold also for matrix functions. So the scaling and squaring methods are based on the property that this identity, which also holds for matrix functions, which means that you can apply this rule several times, and you obtained like a power tower of a matrix that is a matrix exponential of some other matrix, which is scaled. And this matrix exponential here is potentially easier to approximate than the original matrix exponential, since you have a smaller norm or spectral radius. So you can use, for example, those methods down. Yes, and so I'm going to present you a framework somehow, or a software, and it includes some of these method classes, and in particular those two. Yeah, polynomial rational approximation and scaling and squaring methods. I guess you could see quadrature methods also as a part of this, but we don't use it. Okay, and so before, so here's one slide for the experts who maybe wonder if we actually get something better in the end. So we have here is a table with computation time results for the matrix exponential. So I will go through this table once again at the end of the talk, but let me just indicate that we do get better results. So if you do the matrix exponential here for some matrix, you have this computation time, and if you do compute the matrix exponential with our approach, with the same, essentially the same backward error, you can do it faster. Not a factor 2 in this case, but substantially faster. And you also see interesting things here, like so the difference between XM in MATLAB and the corresponding thing in Julia is not that big. So except that you have to use MKL, not OpenBLAS. But yeah, so I just want to show you that we do have some computation time results that we think that we are happy with, and this table could be made even larger, or we could make even larger matrices, but then we had some of these methods ran out of memory, so we didn't. So we could stop at 2000. Okay, but that was like a sneak preview of like the end result, and so let me back up a little bit. And we have like a computation graph viewpoint. This is like the core of this result, and it's so it starts from an observation. Not so difficult to convince yourself that many methods in this class of methods can be expressed as graphs, computation graphs. So, for example, the scaling and squaring algorithm, where you use a Padé approximant. So here is, I wrote it 2 to the power p here, but it's a power tower, and here is a Padé approximant of the scaled matrix exponential. So, and that's the Padé approximant. It's just a polynomial evaluated in some way. And so it's just, so note here, so it's just, you have to evaluate Q, you need to do multiplications of the matrices, and then you need to do one left division. And then you need to sum things. So that's the operations we're going to need later. And so you can form all the operations that I've written here into a graph, where, so I have a color coding where, so red means multiplication, and blue means forming a linear combination, and the dashed line means left division. So we see here so here in the center we build the monomial coefficients, and then this outer part here is forming the numerator and denominator, and then you do the Padé approximant, and then you square it twice. So it's just a visualization of the same procedure as you do in scaling and squaring with the Padé approximant. And so a little bit more detailed. So we have with our graph viewpoint will involve only 3 operations. So we will have multiplication of 2 matrices, left division, multiplication with a left inverse, because that's how it's done, like in the lower level routine. You don't compute the inverse first and then multiply it. You actually multiply it with the inverse. And then you have forming linear combinations of 2 matrices where these alpha and beta are 2 given coefficients, scalar coefficients. So to go back here, every blue line corresponds to a linear combination with some scalar coefficients that I haven't given. So every blue line is some scalar coefficient, for example, given by the Padé approximant expansion. Yes, and we form here formally is a directed acyclic graph, and so we've chosen these 3 multiplications because it makes our life easier. In many cases, you can of course imagine that you have more terms here or something, but it just makes more code and doesn't increase the generality. So as usual in this computation graph viewpoints, you have a topological order. You want to compute the nodes, the values in the nodes in a particular order, and yeah, so we have control here over the order of execution, and this turns out to be important. If you, so this freedom that we can execute it in different orders, as long as it's topological order, gives us improvements of memory improvements. But yeah, so we have written this graph system into we implemented a package, and where we have a lot of features. Here are a couple of features, and so this is a general class of so it's a framework, and we have implemented many of the matrix function algorithms out there in this framework. So if you matrix exponential, obviously, but also other like a square root and sine function are also in there in various versions. And yeah, so we have we want to work with the graph and make it easy to work with the graph, so we can store it, and so we have input like file storage, and we also have a number of analysis tools. So we can do like a round-off error analysis of the graph. Yeah, so we can in some sense compute the round-off error introduced in every operation and get a bound on the error in the end. We also have some backward error tools. I'm going to dig into that a little bit later. So, and the coefficient optimization, that's like the next topic here in this talk. But I want to mention one more like important thing for performance here. So we've written this package in Julia, and we have features. So we represent our graph in a data structure, and we load it into Julia, and but we can generate code in other languages, because of course MATLAB is more used than Julia, or C also has some advantages. So although we work with Julia and we make all the manipulations and everything in Julia, you can take advantage of this package also if you're a MATLAB, if you prefer MATLAB. And yeah, so I like the Julia language a lot. I mean, I use maybe 50% Julia and 50% MATLAB in my everyday work. And but we decided to go for Julia in this work for a number of soft reasons, like it's a somehow coolness factor. I don't know. I enjoy coding in Julia more than in MATLAB, but there are two like a little bit stronger reasons. And so Julia has very good support for high precision arithmetic. So the data type called big float is implemented very carefully, and you can do efficient operations, or quite efficient operations, with big floats, even if they are in matrices or vectors or tensors, if you like. And there's also one advantage in terms of efficiency it's called dot fusion. And so, for example, if you add many matrices together in Julia, this will be done in a clever way. So rather than adding one matrix after another, it will form the whole sum at once. So then this is called, or it's a more general technique called dot fusion, which you don't have in BLAS, for example. But yeah, before yes, okay. So one more thing I said. So yeah, code generation here is important. And one reason is that memory is important nowadays, right? So it's because if your algorithm uses less memory, it's a good thing, and for these dense methods, it's crucial that you use as little memory as possible. And with code generation, with this topological ordering, we can reduce the memory footprint and increase the efficiency quite a bit. Okay, but so here is like some demo that I have prepared beforehand, and so just for those of you who are not so comfortable with Julia, so I only have 4 lines of code here in Julia. So if you want to use our package, you write using GraphMatFun, and this line here, it loads a graph, an object called graph, and this is the native matrix exponential implementation in Julia. So it's a scaling and squaring algorithm. So you have a graph object, and this gen code generates MATLAB code and C code. So Yeah, so it generates a file, myexpm.m and myexpm.c. And so if you hear is the MATLAB prompt, and so now we take some matrix, and we compute the matrix exponential with the xm, and here's with this the code generated by this command here. And okay, so it works, right? So it's kind of a small error, and it's the computation time is also competitive. I don't want you to interpret this simulation too much. I have more serious simulations later, but I just want to show you that we get something competitive. Yes, and so that's if you like MATLAB. If you like C or BLAS, we also generate, and we try quite carefully implemented BLAS code. So where we really take care of that we don't allocate too much, and and make the proper, the correct BLAS calls. Great, and so so I left out one thing here, which was a graph of a coefficient optimization, and so we have a framework now to represent the graphs and work with graphs, but we want to build better algorithms, and so we will do some form of optimization of the graph. And the approach we take here is like a fixed topology approach. So basically you take some graph and you see all the linear combination coefficients as free variables. Yeah, so all the scalar coefficients that I put in the graph, so all the blue lines, they correspond to some coefficient, and we see those as free variables. And so we have the graph is parameterized by all these coefficients. And basically we want to build a better graph based on that. And so essentially we want to, so for a given function, we want to minimize the error. So this depends on the matrix A. So we have this, we use this inequality here. If you have a diagonalizable matrix, you can turn the problem into a scalar problem at the cost of introducing the condition number of the eigenvector matrix. And so I should say here, so we will use this inequality in our design, but later on we also do a backward error analysis. So even if you have something badly conditioned, we are certain that we have that method works well, because we have a backward error analysis as well. So this is only used in the design phase of our approach. So this is an optimization problem essentially over a disk or the boundary of a disk if you're analytic, and so we have a min-max problem. So we want to minimize the largest error on this disk, and we see this as a general optimization problem, and of course there are like a lot of approaches you could imagine to make this small. We tried a lot of approaches, but we didn't get so much better than like a standard approach that we just, so you do some discretization of your boundary of your domain. We did a regularization of the norm and apply a locally convergent optimization routine. And so essentially you get you replace your problem by this, which is a nonlinear least squares problem. So we've turned our min-max problem into a nonlinear least squares problem, and which you can approach with any iterative method for nonlinear least squares problem. Gauss-Newton turned out to work. We didn't get so much better than a Gauss-Newton approach. And Gauss-Newton is, of course, so it requires the evaluation of the Jacobian. So the Jacobian in this case becomes, so it's the derivative of the graph with respect to the coefficients. Since we have represented our problem as a graph, we can compute derivatives, and in some fields this would be called backpropagation. Basically, you traverse the graph once forward and then once backwards, and instead you can compute the total derivative by considering local derivatives of the individual operations. So because of our representation of the problem or the method as a graph, we have access to derivatives. And that's it kind of. So you have your min-max problem, and you try to make the error small using one of these methods. And so here's an example, and I've taken this matrix square root, and one of the classical methods for the matrix square root, which is the Denman-Beavers iteration, which involves basically inverses and two variables and some inverses. And so here's with 10 iterations, the computation looks like this. So you start with identity and A, and then you compute the values here, and the output is your final value there. So our idea is that we take this graph, and now we take all the blue lines and we try to tune them. And so if you do that, so you take all the coefficients and put them into a vector and tune those coefficients, then the error is reduced like this. So here's the graph of, so it's 4 steps currently, and you get an error which is like 10 to the minus 7 or something in this disk. And after optimization, we get an error which is 10 to the 16, so full precision essentially. So after, so we take we do a fixed topology approach. So we take the computation graph of Denman-Beavers iteration, and we try to we change the coefficients to make the error small. And note here that we haven't changed the computational cost. So this is the standard Denman-Beavers, and here is like we have optimized versions, and they are just the same, except that some coefficients are different. Yes. Okay. So this I'm like a linear algebra guy, right? I mean, I'm not alone probably in making a journey into machine learning over the last couple of years, so I want to put this also a little bit in the machine learning lingo here. I want to make some connections here. And okay, so we have a computation graph based optimization approach in our package, and this is also very fundamental in the deep learning frameworks, so which are tremendously successful for certain problems, right? So all these frameworks are based on building computation graphs and doing optimization, typically stochastic gradient descent methods. And okay, so is this the same or is it not? Why don't you use TensorFlow or whatever? And we have our reasons, and here are the reasons. Well, the biggest reason is precision question. So we want to have something which is super accurate, and this is typically not the setting in a deep learning framework. They're typically quite happy with doing things in not so accurate precision, and they're okay with a large error. We would typically in this setting we want like a error which is machine precision. That's the goal. And the other big difference is over which data you're fitting. So we have an optimization problem where the data is essentially points in C, on the disk, and this corresponds to, say, whatever you're training over in your deep learning framework. So we have something in R2 and they have something in like RP squared. So there are many reasons why you would design things for this case, and it wouldn't make sense here. And since we have this, we only have data points in C. Jacobian computation is allowed. So these tricks with mini batches, stochastic gradient descent, and so on, doesn't fit as well with what we're doing. But we do have a number of things in common, and we did try a little bit, but we weren't able to get anything better than our own setting. There's one more machine learning connection here, and so we have worked on so this is our package, GraphMatFun, and then there's a Julia package called Scientific Machine Learning, and so scientific machine learning is something like, you combine the best of simulation tools and machine learning, and so it's a lot about solving PDEs and ODEs, and of course matrix exponential there appears there, so we have improved the implementation here of this using our package. Okay, but let me I don't know, maybe I can stop a little bit and take some questions if there are some questions.
May I ask a question?
Mm-hmm.
Yes, yeah. I was wondering, so your computational graph has a partial order, right? Somehow I missed how you turn the partial order into a total order. Because you need to do that when you optimize the coefficients, right?
What do you mean total? We have a topological order. I mean, so that's, or what do you mean? So maybe there's some terminology here I'm not familiar with. So total order. So.
Well, I mean, the graph gives you just the partial order, right? But then you have to execute, since you don't seem to do parallel computation, you have to do one thing after another, though,
yes.
right?
Yeah.
Turn the partial order into a total order.
Okay, so yeah, that's what I mean by topological order. So yes, so so I mean, this is like a central problem in compiler design, right? So that's exactly what they're working with. So trying to find a way to execute the graph, an order to execute the graph where you're kind of minimizing the memory that you need. So we read about some heuristics to do that. I mean, so it's an NP hard problem. So but yeah, so we have a routine to find out you always have one starting point, right? So you just walk the graph from there. So it's easy to find one topological order, but to find the one that's best is harder.
And then do you keep the same topological order when you optimize for the coefficients?
Yeah, that doesn't matter so much. So yeah, but we keep the same. I mean, you want also the optimization routine to be fast, so you typically keep the same topological order. Yeah.
Can I just also ask, when you try to calculate the Jacobian of Q, how are you doing that? Are you using dual numbers in Julia, and how does that interact with
so we
routines?
Oh, sorry.
How does that interact with BLA routines for these calculations?
Yeah, so we don't need to use BLAs there because we're only working on the scalar level. So yeah, we don't have matrices basically when we're doing that optimization.
Mm-hmm. Yeah.
So yeah, so you just need to walk the graph back and forth with scalar entries in your graph. So yeah.
Great.
Okay, let me continue. So yeah, so we wanted to apply this to the matrix exponential, of course, or that's the most important application. So we wanted to improve that, and scaling and squaring is kind of the state of the art for the matrix exponential, and the version of scaling and squaring that's been seen as state of the art for quite a few years, as far as I know, is Padé approximant. And yeah, so I mean, you can trace it back to the 70s, but so the current implementations are based on work from these authors. So a Padé approximant, right? So that's has been state of the art for quite a few years, but now we have a number of results from some groups in Spain where they do some very clever techniques based and only do polynomial evaluation. Yes, which turns out to be very competitive. They claim to be even more competitive, and I'm now, we are, based on our simulations, it seems that they are indeed correct, but polynomial can be better than rational. But okay, let me back up a little bit here. So like comparing these rational and polynomial evaluation schemes is a little bit complicated because it's like apples and pears. You have what's the computational cost of inverting a matrix, and there's no right answer here. So how much more expensive is it to invert a matrix? It depends on the architecture and a lot of other things. But based on some asymptotic analysis, this is like the standard way to compare how the computation cost of inversion and multiplication. So typically you normalize the computation. You say that the cost 1 is multiplication, and then 4/3 is a left division. So multiplication and left division is essentially the same, but a little bit more for left division. And then this is important. So addition or forming linear combination has 0 computational cost. Okay, and then you can start comparing here if you assume this holds. And in terms of these canonical computation units, they have some convincing results that they can be better than the Padé approximate with scaling and squaring. They still do scaling and squaring, but it's Taylor approximate of the red matrix here. Yes, but okay. So I think we have managed to be better than these also based on what we're building on their results. Yes, I wanted to mention here also. So we have this is so the implementation in MATLAB is based on this rational. And also Julia and TensorFlow, but actually in PyTorch they have taken one of these methods here, and so that's the default implementation in PyTorch. It's a polynomial evaluation scheme, and so there are some advantages with polynomial evaluation scheme in terms of parallelization. For example, there it's just a lot more easier to implement a matrix multiplication than a left division. But yes. Okay, so we based on their results here, we said, okay, so let's focus on polynomials, and so keep in mind now that you have addition forming a linear combination of two matrices has 0 cost. So here is like an economical way of doing polynomial evaluation. So if you so notation here A0, A1 are just identity and A. So if you have A0 and 1, okay, the only thing multiplication you can do here is to add these two together and multiply it with another linear combination. So this is like all the things you can do with just one multiplication. Yeah. Okay, you could add something here, but it will be incorporated later. So essentially, this is everything you can do by just using one multiplication. Okay, so that's A2, and then at the next level we have 3 matrices, so we can form. We have 0 computational cost to form a linear combination. So we take any linear combination that of what we have computed so far and multiply it with any other linear combination. So this is again the most general thing you can do using only 2 multiplications. And then you continue. So after m iterations, you have m terms here, and you multiply it with m terms here. So now we build this A0 to A2m, and the final thing you do to get the output here in this scheme is to form a linear combination of everything you know, which is also at 0 computational cost. So this is like a method to evaluate polynomials, and I haven't said anything about this coefficients here, and they are seen as free variables. So you can think of any coefficients here. So, and just based on taking the worst case, you can see that this polynomial here will be of degree 2 to the power m. Yeah, so if you do this scheme, you do m multiplications, you get the polynomial which is of degree 2 to the power m. And this is what will be the foundation of the work we did on the matrix exponential. And so for credit reasons, so there are some of these, some similar ideas already in the 70s in this proof. I was very happy to see that. And we can see this also as a generalization of some of the work that's done in Spain. But so if you compare with the work in Spain, then so it's it's a big challenge, so it's very difficult to determine these coefficients such that we have a good approximation. So we want to compute the coefficients that gives you like the best approximation of some given function. And so this Spanish group, if I can call it that, they use symbolic computations. So they see this the variables as free variables, and then they insert it in. They use MATLAB, and so symbolic toolbox in MATLAB. They get the multivariate root finding problem, and they can sometimes solve it. So not always, but yeah, if you do it correctly, they can get some results. But it works. But sometimes they have to change the coefficients in some way, so to make the symbolic computational tool works. So, yeah, so that's how they do it. And in our approach, then we have this optimization framework, and we can encode this graph, this scheme into a graph, and see the variables here as free, and just run our optimizer. And so that's our approach in this. But yeah, let me. There are also some interesting theoretical properties of this set here. So I said that this is, when you do this scheme, you get polynomials of degree 2 to the power m. And I will call the set of polynomials that you can obtain with m multiplications. I will call that, put a little star here. Yeah, so it's a subset of pi to m. And yeah, so this set here, it has the number of parameters. So somehow the degrees of freedom of this set is m squared. Could be smaller, but it's at least it is m squared. So because you have basically two triangular systems here. So it's with m multiplications you have m squared coefficients, but the degree of the polynomial is 2 to the power m. So you realize here you have a problem. You have the number of parameters, the number of free parameters you have is not enough to parameterize the polynomials of high degree. So if you do 10 multiplications, you will have 100 coefficients to tune, but you have something 2 to the power 10, a polynomial of degree 2 to the power 10. So the set is restricted. Yeah. So this should be the other way. No. This is a subset of pi to m. And then you can ask like theoretical questions. So which degree n is does it actually cover? So what is the largest polynomial degree that you can express with a fixed number of multiplications? And we also need some approximation and interpolation, and other things have not been studied here for this topic. Okay, but so I want to stress this again here, that this is a very general scheme, and it's so general that I claim that any polynomial evaluation method can be expressed in this form. So if I take all these alpha and beta coefficients that I had on the previous slide and put them into a table like this, I can, for example, do like a monomial evaluation. Then I have to pick these coefficients. So if I take C0 to C11, I put them here on the bottom evaluation, and then I need to put these values in the triangular systems. And so that's the monomial standard evaluation. If you want to do Horner, you need to put the coefficients in a different way, select them in a different way. But you can also do it, yeah, Horner scheme, it's like that. Patterson-Stockmeier method can also be implemented in this. Then you need to put the coefficients in this form. So I argue that any polynomial evaluation scheme can be expressed in this with this, we call it the degree optimal, the highest degree optimal polynomials. And so I hope the next step is clear what we did. So we use this our package to optimize these coefficients. So we could start, for example, with Patterson-Stockmeier evaluation of the matrix exponential. So that's our starting value, and then we optimize all these coefficients and try to get something better. So we have we take like an evaluation scheme and embed it in this form and optimize the coefficients. Yes, so I have a couple of 2 more minutes here, so just with some computational results. Here's like a comparison with this work of our Spanish colleagues, and they have a Taylor-based approach. So they try to approximate the Taylor series, which means that they have very accurate approximation at the origin. But so we argue that this is not really what you want. You want an error which is evenly distributed because it's a min-max problem. So our optimization here is we have some target disk, and then we can push down the maximum error. So our optimized version, maximum error is smaller than their approach. So this was with 4 multiplication. With 5 multiplication, you can see a bigger difference, and the more multiplications you take, the more the difference. Okay. So here is the table again, and so just what didn't I say? So SID here is the Spanish group, so one of their papers, and so according to our simulations, they are indeed faster than the scaling than XPM. So yeah, yeah, so our approach in our simulation seems to beat that, but the reason is it's just that. For this matrix, we have this computational cost unit is smaller in our case because we managed to approximate the problem in a larger domain. Okay, now I have couple of things about backward error, but I don't have so much time, so I will skip this slide and just show you a table here. So we do have a backward error analysis, and this is a much stronger support of these methods in this class than computation time, in my opinion. So basically you have these theta values, which are backward error thresholds. So theta is represents some form of disk, and within that disk you have a guaranteed backward error. And so you want larger disks. Yeah. So for a fixed number of multiplications, you want as large disk as possible. So if you look at our approach here, we see the theta for our approach is approximately 6, and okay, it says X Julia, but it's actually just a scalar standard scaling and squaring approach. But and so we have a larger disk with essentially the same computation time, and we also have larger than our Spanish colleagues. And yeah, if you could extend this table. So if you go computation costs 6, so you have 6 multiplications, then we have something of size 14, and with this approach here, you get something with approximately error 10, or the disk is of size 10. So we get the same larger guaranteed disks of radius with backward error guarantee with less computation time. Yes. But yeah, so I want to point out here that we have one disk which we optimize over. So we do a target disk with some radius, and then we do a backward error guaranteed disk, which can be something different. Sometimes it can be larger and sometimes smaller than your optimization disk. So you're trying to do build the forward error, essentially small in some region, and then for that graph which you have computed for optimization, you compute the backward error radius. So we are confident that within this disk we have a backward error which is of order of magnitude machine precision, and that it doesn't matter if it's Jordan block or not. So yeah. Great, but that was my last slide. Thank you very much.
Thank you, Elias. Any questions? We had one question in the chat. I'm gonna ask.
So I was wondering if you can say anything about the derivative log function.
Derivative of, say again?
Derivative of the log function.
Of the log function. So if you do the matrix logarithm, or what do you mean?
Matrix log.
Matrix logarithm, yeah. So, okay, so if we can say something about the derivative. Well, so we did implement one of the methods for the matrix logarithm. So I guess we could compute the logarithm, yeah. The derivative of the logarithm. I mean, yeah.
Okay, Federico asked the following question. So the reduction in CPU time comes uniquely from the fact that you get machine accuracy on a larger disk, and hence you need fewer scaling and squaring steps. What about functions other than the exponential?
Yeah, so we had I showed you this matrix square root, and yeah, for that's a much easier problem to beat what we find in the literature. So for that, we really get a smaller error in a larger domain.
So when you do the coefficient optimization, right, was on slide 10. So there was the next coefficient is equal to previous coefficient minus delta k. So is that some sort of greedy algorithm for the optimization of the coefficients?
Yeah. So it's a locally convergent. I mean, it's a locally convergent algorithm. So it's which means you need a good starting value, right? So we of course we present our stuff here as we have new methods, but we're building on other people's graphs. So for example, this Spanish group, they have we implement their method and in our framework, and then we use their method as a starting point of our optimization routine. So it's it's locally convergent method based, starting with the coefficients that they have in their method.
Okay, Bo has a question. I'm trying to unmute you. Can you do it yourself?
Unmute.
There we are.
Oh, no, okay. Okay, Elias, thank you for a very interesting talk. Have you made any comparisons with the triangularized based methods at all? You see, we worked quite a lot on that over the years, and we also worked on recursive block methods based on the commuting properties of the functions of matrices.
Yeah, we haven't done so much comparison. It's difficult to compare in a fair way these different type of method classes. It depends on so many different things. And our thought was that, okay, scaling and squaring for the matrix exponential is state of the art. So let's start with that, and let's see if we can do something better than there. I guess for the matrix, for the square root, I guess you have these other triangularization based methods that maybe can be better.
So when you say state of the art, what do you mean by that? I mean, you say
yeah. Yeah, what do I mean? I think so. What's conceived as the best? I don't know. So for scaling and squaring, I see this for like a dense problem. I think doing scaling and squaring. I don't know of any better method. I'm happy to hear someone else.
Well, I mean, once again, the matrix triangularization, and then you can do.
Yeah. No, but yeah, okay. So yeah, okay. We could do comparisons. Then it will depend on how fast your sure decomposition method will converge. So well, okay, and I can make it good or bad for depending on how fast the QR method converges, for example.
It exists fast methods for that nowadays too, parallel methods and so on.
I know, I'm just claiming that the comparison is kind of difficult because, so that's something, I could create a problem which is hard for one method class and easy for the other, and I could create it for the other.
One thing more, because it's sort of related to this. Somewhere in the problem, in your presentation, you mentioned the condition number of eigenvector matrix there.
Mm-hmm.
So this is maybe a stupid question, but do you have any problems with multiple eigenvalues or close eigenvalues? Does that I mean, maybe it has nothing to, I mean, your method doesn't care about that, or what?
Daniel Kressner asked exactly the same question when we held this talk some time ago. And so for the matrix exponential, because we have the support of the backward error analysis, we haven't seen any problems at all with this, repeated eigenvalues or like a Jordan block would cause any.
But I don't see that the Jordan block by itself will cause any problems. I see when it's not clear if you have a Jordan block or not and stuff like that.
Yeah, when you're close or something. Yeah.
Okay, thank you very much for your replies. How do you get rid of this thing?
Wait, I think I can do it for you.
Okay,
Hans,
thank you.
You had a question? So. Hans, you still need to unmute.
Yes, sorry, I muted myself when the question went on. I use power series for pseudo-inverses of very small matrices, and it lends itself very well to, since I know the size and the condition number of these matrices, or at least bounds on them, it lends itself to it. Have you looked at power series type expansions for pseudo-inverse?
No, pseudo-inverse, we haven't looked at
Okay,
that.
I'll follow up then, thank you.
Yeah, okay.
Okay, any other questions? I can't see any, so let's thank Elias virtually at least.
Okay.
Nice
Thank
talk.
you. Thank you.
And let me see. I'm just gonna post a link to the ENLA website on the chat so everyone can see the next two talks that are currently scheduled. So we have Alison Ramage speaking on March 30, that would be in 2 weeks. And then on April 13, we have Jack Dongara giving a talk. Thanks everyone for attending and hope to see you again in 2 weeks' time.
Okay.
Bye-bye.
Bye-bye.